Hello. In the previous video, we had seen an introduction to critical sections. We had seen that in order to solve the critical section problem, there were three requirements. First is mutual exclusion, second progress, and third bounded weight. In this video, we will see some software solutions for the critical section problem. So, let us start with the most simple solution, that is by disabling interrupts. So, this solution is only applicable for single core systems. With multi-core systems, essentially because of the advanced programmable interrupt controllers present in the systems, interrupts are routed to several processors. Therefore, this solution will not work on multi-core systems. On the other hand, for single core processors or single core systems, disabling interrupts will work. Essentially, we had seen that if interrupts are disabled, then it would prevent context switching, and preventing context switching would mean that the critical section would be not preempted during its execution. Let us look at how interrupts can be used to solve the critical section problem. So, we have the two processes, process 1 and process 2, and they have this critical section which is shown in red. In this critical section, both processes access or modify the same shared data. In order to ensure that the critical section problem is solved and that both processes do not end up in the critical section at the same time, we disable interrupts before entering into the critical section. While on the other hand, while leaving the critical section, the interrupts are enabled again. Disabling interrupts, as we have seen, will prevent the process from getting preempted at the end of its time slice. Essentially, there would not be a timer interrupt that would occur, which would prevent process 1 from preempting. Therefore, we see that this is a very simple solution, and process 1 will continue to execute without any other interrupts occurring as a result of the disabling of interrupts. Similarly, when process 2 enters into this critical section, it disables interrupts, and on leaving the critical section, it enables interrupts again. So, this application of disabling and enabling interrupts is similar to the locking mechanism before entering the critical section and the unlocking mechanism at the exit of the critical section. The locking will ensure that only one process enters or executes in the critical section at a given time, while the unlocking mechanism, that is when interrupts are enabled, would then allow other processes the chance to enter or execute in the critical section. So, this method of solving the critical section problem is simple. It just requires a single instruction in order to disable or enable interrupts, thus preventing context switches from happening. However, the limitations of using interrupts is that it requires a higher privilege level. So, normal application programs which run in user space will not be able to disable and enable interrupts in such a way. Therefore, this solution is only applicable for code that runs in the kernel. So, it is only the kernel or the operating system that is allowed to disable interrupts and enable interrupts again. Therefore, this solution is only applicable for operating system code. And as we have seen before, this disabling and enabling of interrupts is not suited for multi-core systems, essentially because when interrupts are disabled on a multi-core system, it would mean that interrupts corresponding to that core alone is disabled. On the other hand, interrupts are still allowed on the other cores which are running. Thus, on a multi-core system, when disable interrupts is invoked, all interrupts to only that core or that core in the processor is disabled. Other processors, such as a processor which is running this process 2, will not be affected by the disabling of interrupts. Therefore, this solution is not suited for multi-core systems. So, what we will do next is we will try to actually build our own solution for the critical section problem. So, we will start with a very simple solution, we will see its drawbacks, and then we will gradually modify that particular solution until we reach a point where we have solved the critical section problem. So, let us look at this. So, let us start with our first attempt. So, let us say we have this critical section in process 1 and this critical section in process 2, and both these critical sections are manipulating the same data. In addition to this shared data, we also define an other shared data known as turn and set this value of turn to 1. So, what happens? We look into more detail. So, when process 1 begins to execute, it sees that turn equal to 1, therefore, this while loop immediately exits and the critical section gets executed. Now, during the time when process 1 is in the critical section, when process 2 arrives at this particular point, it sees that turn equal to 1 and therefore, it will continue to loop in this particular while loop. The only time that it is capable of exiting from this while loop is when the first process sets turn to 2. So, when the value of turn is set to 2, and remember that turn is a shared variable, therefore, this while loop in process 2 will terminate and process 2 will then enter into the critical section. At the exit of the critical section, process 2 will set the value of turn to 1. So, setting the value of turn to 1 would mean that process 1 can then enter into the critical section. So, essentially when we look at the locking and unlocking mechanism to solve this critical section problem, we see that this while loop present over here is the locking mechanism, while the unlocking mechanism is the third line, that is setting the value of turn to 2. The second observation that we make is that this algorithm or this solution for the critical section problem requires that process 1 executes into the critical section, and then because turn is set to 2 over here, after process 1 completes its critical section execution, process 2 should execute. So, once process 2 completes its execution, process 1 will execute and so on. So, essentially there is an alternating behavior for the critical section. First, process 1 needs to execute the critical section because the value of turn is equal to 1. Then when it completes, it sets turn to 2. So, process 2 will execute and process 2 will set the value of turn to 1 at the end of its critical section, which will result in process 1 executing in the critical section and so on. So, we see that there is an alternating behavior between process 1 and process 2. Quite naturally, because the value of turn is shared between both the processes, and as we have seen, only one process could satisfy this while condition and break out from this while loop. Therefore, exactly one process would enter into the critical section at a given time. Therefore, this solution achieves mutual exclusion. However, there are two limitations of this solution. One is the busy waiting. So, while process 1 is executing in this critical section, process 2 would endlessly execute in this particular while loop. Note that process 2 is in the ready state or the running state, it is not in the blocked state, and therefore, it would consume power as well as time, because it needs to execute in the CPU periodically in order that this value of turn is checked. Another limitation, as we have seen before, it is that this solution for the critical section problem requires that process 1 and process 2 alternates its access into the critical section. So, what it means is that first process 1 should execute, then process 2, process 1, process 2 and so on. So, this creates a problem, especially with the progress requirement of the critical section solution. So, the progress requirement condition stated that if no process is in the critical section and a process requests for the critical section, then it should be offered the lock. Essentially, it should be able to execute in the critical section. We see that this solution will not satisfy the progress requirement. For instance, let us say that process 2 begins to execute before process 1. So, process 2 comes here and it executes this while turn equal to 1, and we see that since process 1 has not yet started, so if the progress condition needs to be met, so process 2 should enter into the critical section, but this is not so. Therefore, this is not a good solution for the critical section problem. The main drawback or the main problem with our first attempt to solve the critical section problem was that it used a common turn flag that was modified by both processes. So, this turn flag was set to 2 in process 1 and set to 1 in process 2, and this forced the two processes to alternate execution in the critical section. So, one possible solution for this, or one possible thing we could actually make better in our second attempt, is to not have a single shared flag. Instead, we will have 2 flags, one for each process. So, let us see the second attempt to solve the critical section problem. So, this is the second attempt. So, unlike the previous attempt, we now have 2 flags present. These 2 flags are also shared among the 2 processes. That means that this flag P2 inside can be accessed from both process 1 as well as process 2. However, it is process 2 which actually changes or modifies this flag. So, process 2 changes from false to true or true to false, while process 1 only reads the status of this flag. It only determines whether the flag is a true or a false. Similarly, the second flag is P1 inside. Now, these flags P2 inside and P1 inside are used during the locking and unlocking of the critical section. Essentially, before process 1 enters into the critical section, it does 2 things. First, it needs to check that the second process, that is P2, is not inside the critical section, and this happens when P2 underscore inside is equal to false. So, if P2 underscore inside is true, it would mean that the second process is executing in the critical section. Then it sets its own flag, that is P1 underscore inside, to true and executes in the critical section, while at the exit of the critical section it sets P1 underscore inside to false. Similarly, process 2 would first execute this while loop until P1 underscore inside is false. So, a value of P1 underscore inside is false would mean that it process P1 has exited from the critical section and is no longer in the critical section, and after it obtains such a condition, the while loop is completed and execution comes over here, where process 2 sets P2 underscore inside equal to true, indicating that it is inside the critical section, and at the end of the critical section, just before exiting, it sets that P2 underscore inside equal to false. Now, this second solution does not require that the 2 processes alternate execution in the critical section. So, for instance, since the initial values of P1 inside and P2 inside are false, suppose process 2 executes first. So, it sees P1 underscore inside equal to false. So, it breaks from this loop and enters into the critical section. Similarly, if process 1 does not start executing, it will keep entering into the critical section without requiring process 1 to execute. However, the problem with this particular solution is that it does not guarantee mutual exclusion. Rather, under some circumstances, it is possible that process 1 as well as process 2 is present in the critical section at the same instant of time. So, let us see when this mutual exclusion does not hold for our second attempt. This particular table here shows the execution of various statements in the CPU with respect to time. That means that this particular while loop executes, and while, since it is in blue color, it means that it corresponds to the process 1, then while P1 underscore inside equal to true and P2 underscore inside equal to true. So, this is in the green color, so it corresponds to process 2, and P1 underscore in and P1 underscore inside equal to true again corresponds to process 1. So, this is how the CPU would execute instructions corresponding to the two processes, and we have like several context switches that occur during the execution, and these are the status of the various flags as the execution progresses. So, let us start with process 1. We have initially said that P1 underscore inside and P2 underscore inside is both false, indicating that both processes are not in the critical section. Therefore, this particular while loop will complete essentially because P2 inside is false. Now, suppose there is a context switch that occurs resulting in process P2 which executes. So, it will also execute these statements while P1 underscore inside is false. So, the while loop will break, and then it sets P2 underscore inside equal to true. Now, immediately after setting this, suppose there is a context switch that occurs and process P1 will continue to execute, and it sets P1 underscore inside equal to true. Essentially, due to the context switch, it will continue to execute from where it has stopped. That is, it had stopped just soon after completion of the while loop, and then it continues with the next instruction over here, that is setting of P1 inside equal to true. So, here we see we have a state where P2 underscore inside equal to true, indicating that P2 is in the critical section, as well as P1 underscore inside equal to true, indicating that P1 is also in the critical section. Therefore, we have not able to achieve mutual exclusion. So, the main problem with this second attempt to solve the critical section problem was that we had two flags, P1 inside and P2 inside. However, they were set after we break from the while loop. That is, only after this particular while loop completes execution and breaks from this, only then are we setting P1 underscore inside to true and P2 underscore inside equal to true. Essentially, what this means is that P1 underscore inside and P2 underscore inside are set to true only within the critical section, and this is what created the problem. So, let us see if we can actually change these ordering a bit. So, we will start with the third attempt, that is the third attempt for solving the critical section problem, and what we will do is just a simple change. So, we will have these two flags. Instead of P1 underscore inside, we will have now P1 wants to enter into the critical section and P2 wants to enter into the critical section. Essentially, each of these flags are set to true when the corresponding process wants to enter into the critical section. So, the minor change we do over here with respect to the second attempt is that process 1 first shows its intention to enter into the critical section by setting P1 underscore wants to enter to true, and only then will it try to determine if process P2 is in the critical section or not. So, essentially it sets P1 underscore wants to enter to true, and then it would execute in this while loop until P2 wants to enter is false. So, when P2 wants to enter becomes false, indicating that the second process has completed execution in the critical section, then process 1 will enter into the critical section. At the end, after the critical section has completed execution, P1 sets the flag P1 wants to enter to false. So, this setting of false will allow process 2 to enter into the critical section. Note that the only difference of this corresponding to our previous attempt was that we moved the flag from inside the critical section, that is after the while loop, to before the while loop. So, what we see is that this particular solution achieves mutual exclusion. So, unlike the previous attempt where we obtained a condition where mutual exclusion was not achieved and we had two processes in the critical section at the same time, in this solution the mutual exclusion is achieved. Essentially, it is guaranteed that when process 1 is in the critical section, process 2 is not in the critical section and vice versa. So, what is not guaranteed is progress. Essentially, we could obtain a state where both processes are endlessly waiting or endlessly executing in this while loop, and we will see how this thing occurs. So, such a state is known as a deadlocked state. So, let us see the deadlock situation in this particular case. So, let us look in this table which shows how the CPU executes instructions with respect to time, and also this table shows the various values of the flags which are present. So, let us start with process 1 executing, and the CPU executes this particular statement and it sets the value of P1 wants to enter to true. Then there is a context switch which results in process 2 executing, which sets the flag P2 wants to enter to true. Now, you see that both processes have set their respective flags to true. Now, when both processes enter into this while loop, we see that in both cases process 1 as well as process 2, this flag is set to true, indicating that both processes will continue to execute this while loop endlessly. Essentially, process 1 is waiting for process 2 to set its flag to false, while process 2 is waiting for process 1 to set its flag to false. So, essentially we have reached a state where each process is waiting for the other process to do something. So, this is what is known as a deadlocked situation, and it could lead to considerable amounts of problem in operating systems. So, to give a more clearer view of what a deadlock is, we have this particular figure here where we have process 1 and process 2 present here. Now, process 1 is in the while loop and it is looping continuously waiting for process 2 to set this flag P2 wants to enter to false. Similarly, process 2 is waiting in the while loop or looping continuously and waiting for this flag P1 wants to enter to be set to false. However, the problem here is that process 1 needs to change the value of this flag, because this flag can be only changed by process 1. Similarly, process 2 needs to change the value of this flag, since this flag can be only changed by process 2, and therefore, we see that there is a tie. Process 1 is waiting for process 2 to change the value of its flag. However, process 2 cannot change the value of its flag because it is waiting for process 1 to change the value of the flag. So, we get some kind of a cycle present over here. So, this cycle will result in both process 1 and process 2 waiting for each other for an endless amount of time. So, this is known as a deadlock. So, in a later video we will look more into details about how deadlocks are caused and how they can be prevented and avoided. So, let us see what the problem was with the third attempt. Essentially, we had the process setting its flag and waiting for the other process's flag to be set to false. And we have seen that because both processes may enter into the while loop and wait for each other, we would have a deadlock situation. Now, the next best thing to do is whenever we have such a deadlock situation, we need to find a way to actually come out of the deadlock situation. Essentially, we need to ensure that exactly one of these two processes will break from the while loop and enter into the critical section. So, this solution was made by Peterson and is what is known as a Peterson's solution, and essentially has an other variable known as favored. So, this is a globally defined variable which is shared among the two processes. Essentially, what the favored variable does is that whenever deadlock situation occurs, it favors one of the processes, and that process would then enter into the critical section, while the other process will continue to wait until the second process sets its flag to false. So, essentially Peterson's solution sets the value of favor to the other process, so that it favors the other process to enter into the critical section. Now, favored it is used to break the tie when both P1 and P2 want to enter into the critical section, that is when both P1 and P2 are waiting in this while loop, or rather are executing in this while loop. The reason this particular solution works is that out of the two processes, there is exactly two values that favored can take. It can take only one or two, and therefore only one of these while loops will actually break or complete execution. So, let us see this in more detail. So, we have seen the two processes P1 and P2, and everything is as the third attempt that we want that P1 wants to enter set to true, and then there is a while loop, and then the critical section, and then P1 wants to enter is set to false. Now, we also have a favored added here in the Peterson solution, and this favored is set to 2 over here, and favored is set to 1 in the second process. So, in all other cases, this particular Peterson solution behaves like our third attempt to create the critical section solution. However, the only difference comes when both processes enter into this while loop at the same time. In such a case, the value of favored will determine which of the two processes enter into the critical section. So, let us say process 2 is favored and it enters into the critical section, and at the end of its critical section it sets P2 wants to enter to false. So, remember that during this entire period P1 is still waiting or still executing in the while loop. Now, when process 2 sets its flag to false, it immediately causes this while loop to break. As a result, process 1 will enter into the critical section. So, you see that only when process 2 exits from the critical section, only then will process 1 enter into the critical section, thus achieving mutual exclusion. Also, we have seen that the bounded wait issue is solved, and as well as the progress thing is solved. The Peterson solution works very efficiently for two processes. In the next video, we will see the bakery algorithm, which is used to solve the critical section problem when there are multiple processes in the system. So, the bakery algorithm solves the critical section problem when the number of processes is greater than 2. Thank you.